everyone. My name is Adv Math. I think most of you already know me. I'm gonna teach the first part of the class, which is 50%, and after that, Dr. Benjamin will teach the second part. In the first part, we are focusing on differential equation, and after that, Dr. Benjamin will focus on the partial differential equation. In this chapter, we are going to focus on differential equation, or we like to say ordinary differential equation. At the beginning of this chapter, we're going to learn the definitions of all the terms that we use in ODE. And then we use different kind of techniques that we use to solve differential equation. Okay, the techniques that we're going to learn in the later part of this chapter is the first one is the difference separation method, and then exact differential equation, and then integrating factor, linear equation, homogeneous equation, and we finish with the binary equation. Most of you already learned these techniques, but we're gonna go through these techniques again just to remind yourself. And all of these kind of techniques they are very important that we use to solve the problems in other classes, such as like when you go to the advanced transport phenomena or advanced kinetics, you have to use these basics ODEs to solve those problems. Okay, let's go with the class material. Okay, now let's take a look at the definition of differential equation. Okay, when we talk about differential equation, it means an equation that contains one or more derivatives of unknown function. Okay, the two kinds of DE. The first one is ordinary differential equation, or we call it ODE. Most of you have learned this ODE before in your first year or second year, which is more simple one, right? And in the second one, which is partial differential equation or PDE, maybe some of you have learned this a little bit, but in this class we're gonna focus on details of PDE, and Dr. Benjamin will teach this section after the midterm. Okay. Okay, this slide shows examples of ODE. ODE means an equation that contains a function of one independent variable and its derivatives. Okay, let's take a look at these examples, and you will know what is the independent and dependent variables. Okay, in the first examples, which is d square y over dt square plus 5 dy over dx plus 6y equal to 0, and the second one is d to the fourth x over dt to the fourth minus 2 d square x over dt square plus 3x equal to cosine t. This is another kind of ODE equation. And the last example is y triple prime plus 3y equal to x. Now take a look at these three equations and take a look and see which one is dependent variables and which one is independent variables. Okay, in the first equation, x is the independent variables and the dependent variable is fine. You know, independent is mean over here, over the x here, and dependent is something that depend on x, so it's y, right? In the second one, Second example, independent variables is t, over dt here. So independent is t. Dependent variables x, because x is depend on t. So this is dependent variables. And in the third examples, here you see y is the dependent variables. It depends on some variables, which is x here. You see x, which is another variable. X here is independent variables. So x is independent variables and y is the dependent variables. So these are examples of ODE. So we have dependent and independent variables. Okay, now let's take a look at examples of PDE. PDE is mean an equation that contains unknown multivariable functions and their partial derivatives. So when you compare ODE with PDE, for the ODE we have only one variables, one dependent variables and one independent variables. For PDE we have 2 or 3 or higher dependent variables, which means like we have multi-variables function. Okay, let's take a look at example you will see. Okay, in the first example, we have curl square u over curl x square plus curl square u over curl y square plus curl square u over curl z square equal to 0 here. In this symbol curl, you can call it d, it's the same thing, which is derivative. It's represent the derivative. But for the PDE we call like curl, so it's kind of sound different from ODE. And in this class we can call this symbol as curl, which is derivative. So in these examples, in the first example, we have one dependent variable, which is u, and 3 independent variables, which is x, y, and z here. So in this equation is a kind of partial differential equation. Okay, in the second examples, we have curl u over curl x plus curl u over curl y equal to x. And this is another kind of example of PDE. U here is the dependent variables and x and y is independent. They are independent variables. Okay, now we know ODE and we know PDE. So now let's take a look at the definition of the order of differential equation. Order of DE is defined as the highest derivative of dependent variables with respect to the independent variables appearing in the equation. Okay, it means just like this symbol. Okay, let's take a look at example. Okay, in the first equation we have y palm plus 2y equal to 3x. So when we look at the highest derivative, which is y palm here, so this is only first derivative, so this is first order. In the second example, which is y double palm, and in this parenthesis to the third plus y palm plus 3y equal to 0. This is y double palm is the highest derivative. So in this equation, it's the second order. Okay. And in the last example, is y triple palm plus 3 to the fifth equal to e to the x. The first term, which is y to the third, y triple palm This is the highest derivative. So in this equation is the third order. Okay, what you learn here, you just take a look at the palm sign here. Like, this is first, only first palm. So this is first order, this is second, and this is the third order. Okay, now let's take a look at the definition of degree of differential equation. Degree of differential equation is the power of the highest order derivative in the equation. So in the last slide we learned the order of equation already. So now we look at the degree of differential equation. You just take a look at the highest order and see what is the power of that at that term. So okay, the power has the lowest positive integer. So that means the power, it has to be a positive integer. Okay, now to take a look at example. This is d square y over dx square in this parenthesis to the third plus dy over dx equal to sine x. Okay, this term is the highest order, which is second order, right? And this one power to the power is the third, which is 3 here. So in this equation, it's degree of 3 with power with order 2. Okay, order 2 and degree of 3. Okay, go to the second example. In this equation is y triple palm in this parenthesis to third minus y double palm equal to. Okay, this is the highest derivative, which is order of 3, and in this is the power, which is 2/3, but it's not uh, integer, so we have to change it to positive integer. So what you do is you just rearrange the equation. So from this we can move it to y triple palm to the 2/3, move this side to the side, which is gonna get 2 plus y double palm. So we have to get rid of this third here. So it's gonna be you on both sides power 3, both side power 3. So it's gonna be this on the right hand side is 2 plus y double palm to the third, and on the right side is y triple palm to the second. So in this equation is the order of 3, y triple palm here, and degree of 2. Okay, so the next definition is the linear or nonlinear equation. When we talk about linear equation, it means all of the dependent variables have the same degree of 1 only. Okay, when you look at each term, it has to be degree of 1 only. So in other case, it's gonna be nonlinear equation. Okay, and the second one is know any terms of a multiplication between dependent variables and or derivative of dependent variables. Okay, so otherwise it's going to be uh, nonlinear equation. So nonlinear equation is mean it does not satisfy the linear equation. Okay, now let's take a look examples of the linear and nonlinear equation, so you will see it more clear how it look like when we talk about linear or nonlinear equation. Now take a look at all these examples and guess each one is a linear equation or nonlinear equation. Okay, in the first example here we have y double prime plus 5y plus 6y equal to 0. So in any term of this, every term has degree of 1 only, and no multiplication products of derivative or their derivative. So in this first example is the linear equation, and this second one is y fourth prime plus x square y triple prime plus x to the third times y prime equal to x times e to the x. So in this equation, it has a degree of 1 only and no multiplication of derivatives terms. So in this equation is linear equation. So in the next example is we have here is d square y over dx square plus 5 dy over dx plus 6y prime equal to 0, and this term is degree of 1, but this one is the multiplication of derivative, so this term is the nonlinear equation. So the next is d square y over dx square plus 5 dy over dx to the fifth plus 6 equal to 0, and this term is not degree of 1, so this is degree of 5. So in this equation is nonlinear equation. So next is the y double prime plus 3y times y prime plus 3 equal to 0, and when you look at this is the term which the multiplication product of derivative and the y. So it's this one is not follow the linear form. So this one is the nonlinear equation. So the next is the curve y over curve t equal to curve square y over curve x square. So this follow the linear form. It has degree of 1 and no multiplication products. And this one is curve y over curve t to the fifth equal curve square y over curve x square. This one is degree of 5, so this one is nonlinear equation. And so now you should know which one is linear or nonlinear equation. And the other form of which is not linear or nonlinear equation is we call it quasi-linear equation. Quasi-linear equation is equation that has nonlinear differential equation, and if there are no multiplication among or different variables and derivatives in the highest derivative. So don't worry about this form because we're not gonna take much time, or we're not gonna learn any form of this quasi-linear equation. Now look at the definition of homogeneous equation and non-homogeneous equation. For the homogeneous equation, and differential equation is homogeneous if every single term contains the dependent variables or their derivative and they are set to zeros. Okay, it means every single term contains dependent variables or their derivative, either one, and they are set to 0. That means they are equal to 0. So look at this example. This one, this term, and this term. The first three terms, they are contain dependent variables or their derivative. Okay, this is the dependent variables, and this one is derivative form, and they are set to 0. So this is a form of homogeneous equation. Okay, so for the non-homogeneous equation, this means a differential equation which does not satisfy the definition of homogeneous equation. So that means if it does not homogeneous equation, it means non-homogeneous equation anyway. So okay, let's take a look at this example. So in the first three terms here, there are dependent variables and their derivatives, right? Or either one. And this one does not contain dependent variables or their derivative, which is 6x plus 3y. This one does not follow the homogeneous equation. So this one is non-homogeneous equation. And you will hear this a lot, which is the general solution. General solution is YC, if you remember. General solutions mean solutions obtained from the integrating the differential equation. This is called YC. So that means when you get the solution without substituting the constant C, that solution is called general solution. And the particular solution, so when we get the general solution and then we substitute with the initial condition or find the solution of the C, the constant, we call it particular solution. So here it's a solution that obtained by assigning specific values of the arbitrary constant in the general solution. Okay. Whenever you substitute with the initial condition or specific values or initial condition, we can get that particular solution. Okay. Okay. Here is the term initial conditions. It means constants that are specified at the initial points, generally time points. Okay, generally time points are called initial condition or IPs. The problem with specified initial condition are called initial value problems. So initial problem, we use this term when we have a problem that specify one point to one point, like one time or one time. So for example, at beginning until the end. So this is the condition that provides its initial condition. Okay. And another term is boundary condition, and which is similar to initial condition, but this one is more dimension. It means constants that are specified at the boundary points, generally space points. It means like, like an area or like 2-dimension or 3-dimension system. They are called boundary conditions. Problems with specified boundary conditions are called boundary initial value problem or BVPS. Okay. So the difference between initial condition and boundary condition is initial condition is about times, one point to one point, and boundary condition is about space points. This is like, distance from A to B, and also in the 2-dimension, which is A, also to Y, for example, in another dimension. So, and boundary condition has more specific value condition. Initial condition just give you from beginning or from the beginning until the end. Okay. So now let's take a look at the examples of the first techniques that we use to solve ODE, which is the most simple one. Is we call here is the separation equation or separation equation technique. So in general term, when we have M, which is containing function of x and y, dx, plus n containing function of x and y, dy. Okay, this is the equation of ODE. Okay, this is equal to 0. So in this equation 1, if we can write equation 1, 2 in this form, which is ax times dx plus dy times dy equal to 0, this is said to be separable. Okay, that means if you can separate x with dx and y term with dy and set to 0, we can use separation technique to solve the problem. Okay, let's take a look at example. We have dy over dx equal to 2y over x here. And first thing what you do is you try to separate x and y with dx and dy. Okay, and you rearrange, you get x dy minus 2y dx equal to 0. Here x with dy and y with dx, so it's not separable yet. So let's try again. You rearrange to get actually dy over y and dx over x. Here you're gonna get this kind of term, which is dy over y minus 2 dy over x equal to 0. Now in this term, y term with dy and x term with dx, this content 2, it doesn't matter, you can move to y or move to x, it doesn't matter. So now you can use the simple integration to solve this problem. So integration of dy over y, we're going to get ln y and minus here, take minus down, and 2 here, so take it down. Dx over x, integration of this, we get ln x. And integration of 0, we got ln c. Okay, don't forget this. So this is the final example, final solution. So the ln of this is ln, this is the minus sign, and this is the plus sign. So we can combine to each other into one form. The minus sign is the divide product. So we get ln y over x squared equal to ln c. And the final answer is y equal to y over x squared equal to c, or y equal to c x squared. Okay, c is a constant. This is the final answer. This is the very simple one, which is the separation equation. So whenever you have an ODE problem, the first thing is you do is you separate the equation. If you cannot separate equation, into this general form, ax dx plus by dy equal to 0, then you have to try other methods. Okay. Now take a look at the second example of separation equation. Here we have 2xy plus 2x times dx minus y dy equal to 0. We also have initial condition or initial value problem, which is x equal to 0, y equal to minus 2. That means when you get the general solution, which means the answer with C, you have to substitute the solution to get the particular solution. Okay, which means you solve C to get the final solution. Okay, so what you do is first you try to separate the equation. Try different way if you can separate this problem. So in this equation we can, beginning we can take 2x out from this parenthesis. We get 2x times y plus 1 times dx minus y dy. Okay. Now what we do next is try to rearrange if we can separate x and y from each other. Okay. So in this term you divided each term with y plus 1. So this one, y plus 1 go away, we cross it out. So in this term we're gonna have y plus 1, right? So we're gonna get 2x dx minus y over y plus 1 dy equal to 0. So now this terms x with dx, function y with dy. So now this term we can use the separation method to solve this problem. So just put the integration into each one. So integration of 2x dx, we're gonna get x squared, right? And in this one, it's getting more difficult. So what you do is you take y divided by y plus 1. So when I'm going to show you in the class, this is how we have to write down how we do it. So when you divided y with y plus 1, we can get y with the rest, which is minus 1 over y plus 1, right? So this is actually it's very easy, but I will show you in the class. Okay. Time dy equal to integration of 0 equal to c, okay, a constant. So in this form, 1 dy integration we get y, right? So and this one we get on y plus 1. Okay, this is from your undergrad. You have to remember of this simple integration. Okay, and so now this is the general solution. Because we have c here, we have to solve to get the particular solution, which is you substituting x equal to 0, y equal to minus 2, and see what is the value of c here. So you substitute x and y here and you solve to get c, and we get c equal to 2 here. So now the final answer is x squared minus y plus 1 y plus 1 equal to 2. Right? This is the particular solution. Okay. Now go to the second method that we use to solve ODE is the exact differential equation. Okay, now let's take a look at the theorem first. That's the function of m, n, and partial m or curve m over curve y and curve n over curve x be continuous in the region of x and y. Then the equation of m, function of x and y dx plus n, a function of x and y dy equal to 0. It is said to be exact differential equation if the partial differential equation of m over partial y or curve y equal to curve n over curve x. Or that means, in the simple way that we say is, when we have a function, this m dx plus n dy equal to 0, and it containing x and y and n containing x and y. If we do partial diff of m function with the dy and equal to a partial diff of n over dx, if this term equal to this term, that means we can use the exact differential equation to solve the problem. Okay, let's take a look at example, then we know what we are doing or how it works. Okay, in this example we have 3x times xy minus 2 in this parenthesis times dx, okay, x here is the x term is the m function. Okay, just remember this form m dx. So this is m function dx plus n dy. So x to the third plus 2y dy. This is the n function equal to 0. So what you do if you wanna prove that this is the exact differential equation? So you do the partial diff of this term, you know, the term with dx with dy, and the term with dx, you know, with the dy with dx, and see the results. If these two results are the same, then we can use the exact differential equation to solve the problem. Okay, so here the partial diff of m with dy, okay, this term with dy, you do differentiate of each term. So this one you're gonna get like 3x squared, right? And this term with dy go to 0, and the second term, the n term with the x, okay, with the x. So this one you differentiate d of x to the third over the x, so you get 3x to the second. Okay, and this term which is containing no x, so it's go to 0, so you're gonna get 3x to the second or x squared. So the results of these two are the same, exactly the same. So this is the exact differential equation. So the next, here I said it here, the partial diff of m with dy equal to partial n or curl n over dx. They are equal, so this is the exact differential equation. So from this you go back again. That means from this problem there should be a term like some terms that coming from this kind of product, which is duv, right? duv equal to udv plus vdu. So that means there's like at least two terms from this, at least two terms from this equation coming from duv. Okay, because when you do duv, you're gonna get udv plus vdu. So when you consider this problem, you're gonna have this term and this term. They're coming from u and v. Okay, in this case u is x squared and y is y, right? So now you can combine u and v into duv here, duv, right? So you can do the simple integration. You're gonna get x to the third times y plus the integration of this term, the rest of the terms. So here is the x only, containing of x only, and here containing of y only. So you can do the simple integration of minus, you take it down, 6x dx. So you get x squared over second. So 6 over 3, sorry, 6 over 2 is equal to 3. And this one you get y squared over 2, the 2 here too. So 2 cos 2 go away, so it get 1 here. So this is the final answer, which is x to the third times y minus 3x squared plus y squared equal to c. This is the general solution. Okay, so just remember this: when you do the exact differential equation, that means there should be 2 terms at least, maybe 2 or 4 terms or 3 terms sometimes, coming from the different the multiplication product of DUV. Okay, and you have to consider each term and find the combination of U and V. The most difficult one is you have to find the right combination. Okay, so now go take a look at the second problem. Okay, second example of the differential equation. Here we have 2xt times dx over dt plus x squared minus 2t equal to 0. Okay, x in this case is the dependent variable and t is the independent variables. Okay, so when you look at this, at the beginning you don't know which method you have to use, but if you want to try the exact differential equation, so you have to separate term of dt and dx, right? So you just rearrange to get the term with dx and another term with dt. So the x term here, we get 2xt, which is the function of m, and the term with dt, we get x squared minus 2t. So now you do the partial diff of each term. Basically, you have dx here, so you do partial diff with over dt, and this one we have dt here, so you do the partial diff with dx, which is more easy to remember. Okay, and this one over the dt, so you get 2x, right? And this one over dx, you get 2x also. This one is equal to 0, right? You get 2x. So the partial diff of each term, they are equal, so equal to 2x. So that means this method we can use the exact equation to solve it. So now you have to find the combination, which is easy. Here we have dx and dt. So this coming from, just look at the highest power. We have x squared here, the highest. So that means the x squared, and another one is t, right? T, the highest power is 1, right? Another one there's no power, which is 0. So that means u and v is containing x squared and t. So you prove it by, you do the diff term of u and v, or diff of x squared times t. You're gonna get this result. So that means u and v is x squared times t, and the rest of the term, which is minus 2t dt here. So you do the simple integration here, you get t squared, right? That minus, don't forget it. And this is the final answer, which is the general solution, is x squared times t minus t squared equal to c. which is the answer. Okay, now you learn the first method is the separation equation, and this one is the exact differential equation. Now we're gonna learn more method later.